Welcome to this explainer. Today, we're zooming way, way out and then plunging right back in to demystify an absolutely fascinating lenticular galaxy known as Caldwell 53, or by its catalog name NGC 3115. We're going to break down some incredibly complex physics today, everything from hierarchical galaxy assembly to invisible cosmic forces. So let's dive right in.
So here's the massive mystery we're unpacking today. How exactly does an isolated galaxy manage to build a staggering billion solar mass black hole, only to somehow knock it completely off-center? We're going to explore how a solitary system achieves such extreme displaced cosmic power and what its invisible energy signatures can actually teach us about the universe.
Section 1. Meet Caldwell 53.
If you're hunting for Caldwell 53, you'll find it nestled deep in the Sextans constellation. It's a lenticular galaxy, meaning it's kind of the middle ground between an elliptical and a spiral galaxy. It's got this brilliantly bright central bulge and a disk, but it lacks the sweeping, star-forming spiral arms we're so used to seeing in our own Milky Way. But to really anchor our scale today, you need to wrap your head around this number. It sits a staggering 32 million light-years away from Earth. That means we are quite literally looking 32 million years into the past. Yet, despite that vast distance, it holds the record as the nearest galaxy to us hosting a billion solar mass black hole.
And you know, that immense distance perfectly illustrates a fundamental aspect of its identity. Caldwell 53 is what we call a field galaxy. Unlike the Milky Way, which is part of a local group, Caldwell 53 is gravitationally flying solo. Because it evolved in total isolation, totally free from the chaotic gravitational tugs of any noisy neighbors, it acts as a remarkably pristine laboratory for us to study pure galactic physics.
Moving on to Section 2. Fossils in the halo.
Before we hit that dense core, we have to pass through the galaxy's halo. And this halo is literally littered with ancient star clusters acting as cosmic fossil records. It tells the story of the galaxy's hierarchical assembly. Picture this. About 13 billion years ago, Caldwell 53 started with a violent, rapid dissipative collapse. Essentially, a massive cloud of gas rapidly cooling and falling inward. Fast forward to 10 billion years ago, and massive central bulge had fully formed. But the outer edges? They took much longer, growing over the last couple of billion years through the gradual accretion, or essentially the absorption of smaller satellite galaxies.
Now, what's super cool here is how the stark contrast between distinct blue and red star clusters reveals completely different epochs of star formation and merging. The metal-rich red clusters were largely forged during that early violent collapse, right in the central region. Meanwhile, the metal-poor blue clusters, those are the remnants of smaller, pristine satellite galaxies that were slowly dragged into the outer halo billions of years later. So the crucial takeaway is this distinct mass stratification. The absolute heaviest, most massive globular clusters are intensely concentrated right near the galactic core. Conversely, the lighter clusters are just scattered way farther out in the halo. This physical arrangement is concrete proof that the galaxy grew from the inside out. The smaller, lighter galaxies that got swallowed up later in the timeline ended up depositing their light clusters across much broader, distant orbits. Section 3. A billion mass black hole. Plunging right past that halo and straight into the old, dense galactic core, we meet the absolute heavyweight of Caldwell 53, a supermassive black hole weighing roughly a billion solar masses. It's active, emitting a very distinct radio signal as it feeds on a flow of hot gas. But here is where the story gets incredibly strange. When astronomers used spectroscopic observations to map the exact center of the starry bulge and then mapped the black hole's radio signal, they didn't match at all. This active nucleus is displaced from the stellar center by 14.3 parsecs. Guys, that's about 46 light-years. How on earth do you physically push a billion solar mass black hole 46 light-years away from where gravity dictates it absolutely should be? And that brings us to our prime suspect theory for this displacement, the gravitational wave kick. Imagine, long ago, during a massive merger event, two supermassive black holes sank to the center and formed a binary system. As they spiraled into each other and finally coalesced, they unleashed a colossal, completely asymmetric blast of gravitational waves. To conserve global momentum, the newly merged black hole fired off in the opposite direction like a rocket. It received a massive recoil kick that literally blasted it right out of its own galactic center. Which leads us perfectly into Section 4, Cosmic Currents and Magnetism. With this kicked behemoth sitting totally off-center, we really need to understand how it's interacting with the surrounding space right now at a subatomic level. When discussing the magnetic fields surrounding these accretion flows, you'll constantly run into standard astrophysical quotes claiming that magnetic fields are generated by the turbulent mixing of conducting fluids. For a really long time, the standard idea has been that churning hot gases or fluids somehow spontaneously whip up these massive magnetic structures.
But we've got to correct a massive misconception here. We need a fundamental paradigm shift. You simply cannot whip, boil, or mix conductive fluids to magically make a magnetic field. It doesn't work like that. The fundamental laws of physics dictate that only electric currents, meaning the actual directional flow of raw electrical charge, can create a magnetic field, period.
To see exactly how this works in a cosmic setting, you have to look at primary and secondary electric currents. As these distinct electrical currents flow through space, they naturally generate massive, powerful magnetic loops. This fundamentally challenges those traditional fluid mixing models. It tells us that when we detect magnetic forces and radio emissions around Caldwell 53's displaced black hole, we aren't just looking at hot gas. We are actually looking at the signatures of vast, highly dynamic cosmic electrical circuits.
To actually prove this electrical dynamic is happening right now in Caldwell 53, researchers compared different spectral energy distribution, or SED models. One model tries to explain the black hole's energy output using only thermal electrons, which basically just represents the raw heat in the gas. The other model adds a population of non-thermal electrons. Now, non-thermal electrons are ones that have been accelerated to incredibly high speeds by electromagnetic forces, not just by temperature.
And when you pit those models against the actual data, the purely thermal model completely falls apart trying to explain the low-frequency 1.4 gigahertz radio emissions we detect from this black hole. It just doesn't work. However, the addition of that non-thermal electron population perfectly explains those radio signals. This is incredible proof. It confirms for sure that highly dynamic electrical currents, rather than just heat and fluid mixing, are actively shaping this galaxy's central engine.
From its pristine isolation and inside-out assembly to a gravitationally kicked black hole powered by vast cosmic electrical currents, Caldwell 53 is just a spectacular laboratory of extreme physics. Which leaves us with a final fascinating thought to ponder. If a quiet, gravitationally isolated field galaxy 30 million light-years away holds this much electrically charged, off-center drama, what other massive, hidden electrical dynamics and violently kicked black holes are currently lurking out there in the dark corners of our universe, just waiting to be discovered? Thank you so much for joining me for this explainer. Keep your curiosity sparked, and I'll see you next time.